All right, welcome everyone. I'm James Banting from SparkGeo. So SparkGeo adopted STAC kind of early on as we saw it both as an evolution of geospatial specifications and fulfilling an important niche for geospatial data. We're a consultancy. We help tech companies and organizations with technical geospatial problems and provide guidance around geospatial strategy. So in order to provide the most accurate and pointed advice and code to our customers, we needed to understand the novel and kind of on the horizon approaches to geospatial data management are. We need to help our customers with their near long-term goals and provide them with a solid foundation for their future goals. We added STAC to a lot of our projects over the past 2 years, and today I'm going to share some of those implementations with you. So we began our STAC journey by trying to build out a STAC catalog for one of Canada's most well-known satellite series, the RadarSat. They pushed up RadarSat Constellation mission last year, which is a continuation of the RadarSat sensors. We didn't have a customer for this and instead treated it as a learning experience. Unfortunately, we didn't have access to the underlying data without logging into the government system managing this. But we were still able to get the metadata information and create a couple catalogs to describe the data and provide access to the government site in order to download the data. This was a pretty fun project and our first introduction to the STAC ecosystem. In building this, we took advantage of Matt Hansen's StatStack project for processing the catalog and of the STAC browser, as you can see here, from Seth Fitzsimmons to make the reading the JSON a bit easier. We rediscovered how much open geospatial data Canada has and how much of it can be brought over to STAC, which leads into our next project. So this was SpotStack. In late last year, we were chatting with some of our friends at PCI Geomatics who were interested in the spot ortho images of Canada dataset for a project they had around digitizing and orthorectifying historical air photos. They asked us to build them a metadata system which they could use to select spot images based on different criteria they needed for their orthorectification process. STAC was an obvious solution for us, and PCI were on board with building this and releasing the catalog. So we ended up building SpotStack, which provides access to spot 4 and 5 ortho images over Canada. So if you need orthorectified imagery in the northern parts of Canada, this is one of the best data sets out there for rectifying your imagery. Another project that we use STAC on is as part of the Canada's Digital Technology Supercluster. So us, along with EarthCast, University of Victoria, University of British Columbia, Geoscience BC, and Microsoft collaborate on something called the Earth Data Store, which looks at capacity building for Canadian organizations interested in remote sensing products. STAC forms the backbone of this project as all incoming data sets are indexed, cataloged, and provided to the users through a STAC API. So when a new organization comes on board, they have an open standard for which they can access all the ingested data. We're using STAC not only to provide users access to the data, but also to show some of the provenance of value-add products, such as indexes and machine learning systems. STAC was an easy choice for this project. It's open, it allows all parties to be involved and to share and collaborate and use the data in the same format. I think I am under my 5 minutes. That was the first time I'm under my 5 minutes there. But SparkGeo, we like to help our clients get the most value for their money, and by incorporating open specifications like STAC, we can ensure that customer data sets will be interoperable and will be able to be consumed by many different people and applications. Thanks for your time today.
Awesome. Thanks so much, James. And I think you probably saw earlier, SparkGeo is one of our sponsors, and we're thankful for them helping make the sprint and the outreach today possible. So thanks, James. Next up, Norman, are you there?
Yeah, hi, Chris. I'm here.
Hey, you want to share your screen?
Yeah, I'll do that now.
Cool. So Norman's joining us from TileDB, which I mentioned in my earlier talk as an emerging cloud-native geospatial format.
Okay, so you should be able to see my screen. Please
Yep.
let me know if you can't. Yeah, so I'm very pleased to be here. As Chris was saying, my name's Norman Barker. We're also pleased to be a sponsor. This is a quick presentation. I'm going to have a more detailed session later on today. A little bit about TileDB before we get started. TileDB is a novel database that goes beyond tables to merge any complex data and beyond SQL to analyze data with any tool, all serverless and at planet scale. So let's see what we're going to cover. So I thought we'd start off with some examples. Before we go into technical detail, it's really good to see a few screenshots of the kind of visualizations you can create with data stored with TileDB arrays on the cloud. Then we're going to talk a little bit more about TileDB as a universal data engine. And finally, we're going to go into the weeds with TileDB and Geospatial. Okay, so here are a few examples. On the left, you can see some SAR data that actually came from Capella. We're going to talk more about that later. And in the middle, you can see a NetCDF representation of mean temperature over time. And then on the right, you can see some data there from Pixel 8, showing that inside the Jupyter Notebook. And then you can see some open AIS data in the middle. On the right, you can see a tree canopy that's represented in LiDAR. And the key thing is that all these different formats, they're all represented in one format, which is the Universal Data Engine TileDB array. Okay. So our solutions, let's just bring these all up. So we are an open source core library, and we have open source APIs as well. But we also offer our commercial solution, which is TileDB Cloud Service. And that's a 100% serverless. It's Jupyter Notebooks running in the cloud. And you can do complex geospatial analysis, such as the kind of stuff I'll be showing with SAR later. So the array model. So we have a dense array, that's your raster in geospatial terms, and your sparse array, which is like your point clouds, or it could be your NetCDF time series data. And the key thing is there, we're showing that we have arbitrary dimensions. Here we have D1 and D2, but that also scales to D1, D2, D3, D4, etc. And you can also access that data using labels. So rather than having to know the offset into your data, you can use latitude and longitude directly. The array metadata is key because that's where we store all our geospatial metadata we use to go understand coordinate reference systems and the like. So you can do rapid slicing on arbitrary dimensions. So here I'm showing that you can do a single slice, or you can do multiple slices at the same time. But if you don't want to be doing this within your code, you can actually go and use your familiar data science tools, and we can represent all the arrays as data frames. And you can go and use your libraries such as pandas or Xarray, or even SQL if you want to. So there was a few years ago, there was a thing about doing SQL and rasters, and you can do SQL and rasters here with TileDB as well. So if you want to do time traveling, then you can do that with TileDB because we support the versioning of the data with our fragments. So each fragment contains a snapshot of the data that's being written at that time. So here we have T1, T2, T3, and then we form those to make a logical view. And that's great for things like doing NetCDF model, where you have both a model time and a forecast time. I'm going to speed up a little bit because I know you want to keep me to 5 minutes. So the actual physical format, these can be stored on S3, Azure, or Google Cloud, or it can even be a local array. With TileDB groups, you can go and group different data sets together as well. So we could have a point cloud and a raster and have them inside the same group. So within TileDB, the atomic unit is a tile. Here we can see a dense representation. And you can also go and create compression schemes on top of that. So you can create a filter pipeline. So I can go and link my filter compression steps to get the data to be optimally compressed. And it's very similar with sparse. So you're still accessing tiles even though you're accessing sparse and dense arrays. When you're using sparse, you have spatial indexing across n dimensions, and we use an R tree for that. It's very important that you go and pick your layout so that the R tree is optimal against your array, so you're not querying too many tiles at once, and we have tools and we can help you do that. Here we're talking a little bit more about time traveling. And time traveling is very useful. It's not just for using like NetCDF model and forecast time. It's also very useful when you want to go and see who's been doing what to your data sets, because you can share these data. The whole point of data sets on the cloud is it's not just you accessing, there'll be multiple people accessing at once. So I think this is where it gets interesting. So we can do parallel IO. So if you're doing COGs, you tend to write that sequentially. Whereas with TileDB, you can go and scale out. So I can go and create my data set in parallel, you know, and I'm only limited by the number of servers that are available to me. And same with reads. Reads are multi-threaded too. So I can do very, very fast access to either local or S3 or Azure. So our APIs are interesting. So we have C, C++, Python, R, Go, and Java, Spark, and Dask, MariaDB, and PrestaDB. And I'm particularly interested in this group are the geospatial integrations. And we have integrations there into GDAL, Raster, Poodle, and we have others planned too, such as integrations into GeoPandas or Data Shader. We have been working for like the last 18 months with Capella Space, with Jason Brown in particular, trying to create Jupyter notebooks running on complex data, which is the SAR data. On the bottom right, you can see an animation of SAR over time. And I encourage you to sign up and access that data using our notebooks through tiledb.com. And you also need to register with Capella Space and access their community developer program. In terms of stack, well, we participated in the last sprint, and you can describe TileDB arrays in stack. We found that we needed a media type, and we proposed that you use application x-TileDB. X stands for experimental. It's the same thing that's used by NetCDF and HDF and others. So you can represent cubes, and you can represent point clouds inside a TileDB array through stack. So why is that great? So you're using stack, you're going to find your data, but you're going to use the same data access API to access all your different modalities. And with that, I'd say thank you, and I look forward to seeing you in the session later.
Awesome. Thanks, Norman. Yeah, and Norman's giving a deeper dive in one of the intro sessions, so definitely join in and dig deeper. Kurt, are you here? I see you. You want to share your screen?
Yep. Can you hear me?
Yeah, and I see myself.
Awesome. How about this?
It's good.
And present. All right. So I'm going to talk about Google Earth Engine in 5 minutes. I'm an engineer at Google, and I'm going to hit start on my timer here. And I work on the Google Earth Engine team, not to be confused with Google Earth, which I do myself. And we work in a problem space where we think of the world as a whole, as a planet, and what can we do to power solutions to make global changes to the entire system to try and improve this planet for all of us. And when we think about what we're trying to do with Earth Engine, we look at, one of the main things we look at is the UN list of goals. So these are things that we try to figure out how can we make an impact on as many of these as we can. We're excited to make a dent specifically in many of them, but also as a side effect, a lot of the other ones that we're not thinking about. We hope that our users are coming up with ways to morph our system into something that can attack those problems. So what is Earth Engine? It's a combination of a multi-petabyte catalog with satellite imagery and geospatial data with some planetary scale capabilities and a whole pile of scientists, researchers, and developers trying to do stuff with it, making real-world applications. Boil it down, it's a data catalog plus computational platform. So it all begins with data, which is what I want to talk to you mostly about today. And we have 35 petabytes of open data for people to get going with. It's being updated continuously. There's 550 plus collections from Landsat and Sentinel to all sorts of stuff, including hurricanes, vector data, the works, with more coming online as fast as we can add it. When you have this data there and you combine that computation, you can start doing things at sort of human scale time in front of the computer, like calculating NDVI graphs over time. Things like that become possible that used to be difficult. So you can take all of Landsat and start crunching through it and coming up with stuff that can make a difference in the world. You can also do fancier stuff. You can start gluing together TensorFlow and cloud capabilities. And in there, you can start doing things like classify every pixel on the planet at 10 meters. And then do that over time and see how things are changing and come up with hopefully some real world metrics that can help people make a difference. One concrete example of that we've worked with is Global Fishing Watch. They've taken BigQuery and Earth Engine, combined them together, looked at the entire history of fishing from AIS and now other data sets, and tried to be able to produce something that countries can make actionable decisions on for their waters and solve the global issue of human food and conservation in the ocean, and try and make economies and environmental protection work together. If you'd like to know more about the details of the platform, I encourage you to take a look at the paper by Gorlick et al. From 2017. It goes into the details of how Earth Engine works, and we're happy to talk more about it if people have questions. So specifically, I'd like to talk about cloud-optimized GeoTIFFs and reading and writing these data sets and keeping track of them as we scale. So with import, the cloud-optimized GeoTIFF work is great. Nice thing is it works just like any other import. So if you're doing a regular import into our system, it's just a TIFF. You read it, and it ingests it and turns it into our own internal data structures, and you're good to go. The regular UI works, or you can do, we have a little JSON file that you can load up and then do it from the command line or an RPC. Exporting, we have a cloud-optimized form. Takes a little bit more work on our system since we have to do a copy of the TIFF to make it into a cloud-optimized GeoTIFF, but it's available. It's been there for a while. Seems to work pretty well. More exciting to us is we now have reading cloud-optimized GeoTIFFs from Google Cloud Storage buckets. So what you can do now is load up as many assets as you'd like. Rather than having to do an explicit ingest and convert to our internal data store, you can directly just use your GeoTIFFs. We think that this is going to make it a lot easier for people with very large catalogs to manage them and change them as they need to without having to go through an ingestion process on our part. So it will reduce latency in terms of getting things available to be in the cloud right away. It also means that you're using the same data for other tools that might directly read the GeoTIFF. You don't have to have one copy for your other tools and one copy for Earth Engine. Now you can just have one. To go with that, we'd like to start bringing in STAC. We have an in development catalog where we actually expose STAC assets. We're looking to use STAC also to help people add to it. We're looking for user to contribute whole STAC entries. We're looking for people to be able to manage their own STAC catalogs with Earth Engine in Google Cloud on their own. There's lots of great tools that we'd like to bring in, and we'd like more interaction between Earth Engine and other systems, and we think that STAC can help drive that. So I'm out of time, and I will leave you with a final picture of being able to have all this stuff there is exciting and very helpful. I got to use this for my own house with the recent fires, where I made an app for myself to watch my neighborhood's fires. So I love that we're all working together on the same problems, and hopefully over time we can make even more powerful tools that combine lots of different systems together. Thanks.
Awesome. Thanks so much, Kurt. Looks great. You want to stop your share? Matthias, you're with us?
Yes, I am still with you.
Excellent. Matthias gets the MVP for length of time with us today. We'll let you go to sleep after this.
I will certainly do, yeah. Okay, you should see my screen now. Okay, so I have no slides today, just my tool. My name is Matthias Mohr. I'm working for OpenYo, but what I'm showing today is mostly my private project, which started on the last software sprint. As an idea, I just basically saw stackspec.org and wanted to see what tools do we have, what data sets do we have, and it's quite a lengthy list, and gets even more lengthy, and not very easy to grasp, like what collections are available and what data is available. And in addition, often it's just JSON that you can see there, and that's not very helpful, of course, and not easy to grasp by users. I mean, it's helpful for machines, but not for humans. And so I started with STAC index. The idea is that we have a list then on stackindex.org that users can contribute to and add everything related to STAC, their data and their tools. So there is 3 parts here, basically: catalogs, collection search, and ecosystem, and of course adding new stuff. And I'll start with ecosystem. So basically it's a user contributed list with everything that is software or websites around STAC. There are several categories you can filter on and programming languages. So if you want to look for validation tools in Python, that's easy enough. And then you can see what's available. Or if you want to host something and need a server in, let's say, Java, then there are options available. Yeah, that's regarding the ecosystem. And then there is a list of catalogs, which you can crawl through. That's both APIs and static catalogs. And also they are available in private and public instances. And the other idea is collection search, which is not implemented yet. The idea is to basically index all the STAC catalogs submitted, so in this list, and that we go through all the links in the STAC catalog and then find all the collections, and then make available a searching tool that can be used based on the collection summaries that are there. So basically first entrance for STAC, because there are many APIs and catalogs out there, but you still need to find them, right? And we didn't have the chance yet to make them all available to Google. And still you need to search every single API for your data. So that's the idea yet. We still need to set up the crawler and make the search available, but that's the idea for the next weeks. And now I want to follow up on the intro session I gave this morning. Basically there we made an example STAC item in the session live, and I promised to make that available on STAC index now. So basically that's an open aerial image, aerial map image, just a random one I chose this morning. And here is the catalog and the STAC item we created. And so now I'm copy pasting the link of the catalog and will add it to the STAC index. I'm choosing STAC catalog, paste the link, it tries to read it and automatically fills me the title, slug, and summary here. You can check that and add a contact email or select whether it's private or not. Submit it, and then automatically you can find it here. So the nice thing about, and maybe the most outstanding thing of STAC index is that it provides a free STAC browser for every catalog added. So if I click on this link, it provides me with the STAC browser. So you can start browsing it. It shows my catalog that I just added and the one item I created this morning. And instantly you have the overview, human readable, about all the metadata that is available. And you can, like it's a COG, you can zoom in and look at the data. That's also available for all the other catalogs here. For example, CBERS, you can go through that and look at random data. The nice thing is the page also generates a Google sitemap and submits it to Google search. And Google STAC browser has schema.org data available, so it will be indexable by Google and should show up in the future in Google if you search for data or in Google dataset search. So that's it regarding STAC index. 3 final takeaways. First of all, please submit your catalogs, APIs, softwares to STAC index. Without data, it's not very useful. Then second, make summaries available in stack collections, because we need that in the future for searching. And without this data, it's not very helpful, and people can't find the collections. And then third, we have private APIs in the stack index, but they are not very well findable if there is no collections available or like publicly reachable. So make your collections public if possible. You don't need to make the actual data or items public, but as far as it is possible, make your collections public so that people can find your data. Otherwise, they might not use it. That's so far from my side. Thank you for
awesome. Super cool. Thanks, Matthias. Super cool to see it. It was, yeah, awesome to see this come from nothing to this in the last sprint. And yeah, I think really shows that future vision of Stack of not just a bunch of files. Avi, I see you. You want to share your screen?
Yep, I'm here. Do you see my screen too?
Yep, got it.
Right. Well, hi. Hi, everybody. My name is Javier de Torre. Thank you very much, Chris, for making time last minute thing here. So I want to tell you guys about data warehouse. We call next generation, and and I'm curious, like $5 per terabyte, kind of like a standard that has. You will see in a minute. But before that, I mean, I'm the founder of Carto. So Carto is a location intelligence platform that enables so a solution for companies, for doing spatial data science, like doing dashboards, or building applications with our stack. We also provide a lot of spatial data for spatial analysis, like like things like demographics, but also things like human mobility, and that's why like obviously the interest in here. But today I want to tell you about data warehouses. So I don't think I need to describe it too much to many of you, since you probably know about this, but think of them as a glorified database specialized for analytics. And those have been existing for a long time, right? But we've seen recently over the last probably couple of years, a big revolution coming in what we call next generation cloud data warehouses. The one that really started the race in a way was BigQuery 10 years ago, and Snowflake, as you might have heard, going to IPO now is also making a lot of sense, a lot of noise. But like kind of like for you to kind of get an idea, there's kind of like one of these data warehouses, I'm going to be talking about in a minute, in each of the vendors. And then there is Snowflake, which is kind of like the independent or multi-cloud, if you want to say. And then in the open source, the closest thing that you can think of is Presto or Delta Lake, right? Apache. Some open source projects in there. Now, the cool thing about the title that came in here is that you can see that this is becoming some sort of like a standard, where you see like these three are already called like a standardized pricing, and they're charging $5 per terabyte that you query data process, right? So all of them already are charging the same. So you can see there's some consolidation in the market, but obviously, like I said, like BigQuery started earlier, and it's probably the one that is most advanced right now. Now, why is this exciting? I like to mention three main things that are like a game changer for our industry and for probably many others. But the first one, you might have heard this concept of compute and storage separation. Essentially, like data, when you store it in these data warehouses, it stays at cloud storage, kind of like S3 or Google Cloud Storage, like very, very cheaply. And then it's only when you query it, when you run your SQL, that then actually you pay for the amount of data that you've processed. So that's a huge game changer, because it means that you can store your data almost for free because it's very cheap, and then only pay when you're getting value out of it, when you're querying it. But that's only one of it. The second that is super interesting is what we call multi-tenancy. So think of it like these databases, kind of like, it's like if you have all the users in a single database and you can do queries between them. You're gonna see this is a game changer in our industry. And obviously a scalability and, like serverless, essentially the idea that, like many of these systems, you might spin up, like hundreds of servers to do in parallel your queries is a big, big thing, now that we're working with very, very large data sets, all of us, right? Now, how they work, not going to go into the details, but, essentially most of them, they expose a SQL interface where you write just regular SQL. And then, like the engine will go to the storage, or will have some sort in the middle, and we'll get the data and then just expose it and, return it back. Right? Now, the beauty about multi-tenancy, as I was describing, just look at this SQL. It's very simple. It's a classical call like a spatial intersection, right, between two tables. But these two tables, one come from one company, and the other comes, for example, in this case, from Carto, our repository of data, right? And I'm doing a live join between two databases, right? And that's, like for any user, in this case of BigQuery in the entire world. So if my data that I have in Carto updates, that Acme user on the other side, their join, their result will also update automatically. So no ETL, no data transformations, it's all there. So that's a massive change on the way that we distribute data. Now, they're also like the perfect engine for consuming things like, vector COGs, in this case, I was going to call it. I'm going to give you a demo of that. So think about something like the Global Biodiversity Information Facility. They publish around 1.4 billion points of records of where species are. Just think on the use case of trying to visualize a data set like this. In the current world, download 1.32 terabytes of a CSV, load it into a database, call it, process it into tiles. And then you know what? It's going to take you like 2-3 days if you're good at it. And how many hundreds or thousands of dollars will that cost? And, and it will be outdated exactly the same time that you got it done, right? So how does this look like on like a native cloud environment? So GViv made this data available, this 1.4 billion in a Google Cloud Storage as an Apache Abro file. It's already done it. It gets loaded in BigQuery in less than 5 minutes. And then within that, then you, in this case, using Carto, you can tile the dataset with a simple query. And now in less than 10 minutes that it has taken, the processing, you got straight away, oh, sorry, I'm just gonna go finally to this map. 1.4 billion points coming directly out of a database, loaded in less than 15 minutes and costing less than $1 of processing. That's really enabling spatial data science at the scale. That's the beauty of this, right? And this is a few examples. I mean, like this is the World Data Vision Protected Areas, around 5 gigabytes of polygons, live from there, loaded the same way. This is the AIS tile set that the AIS data set that we were talking before, same way. This is the data set from Microsoft published about all the buildings in the United States. Like again, loaded in minutes and less than $1 of processing. So that's a huge revolution coming in there. Now, just gonna finish with, I know I'm going there. So before, hours to download, like hours, if not days, for processing, hundreds of dollars. And every time there's an update, you have to start again. Versus cloud native, you've seen it before. Now I'm just gonna wrap it up here. How do we enable this? Well, first of all, data publishers need to start publishing to these next generation data warehouses, likely through publishing already prepared spatial Abro files. Abro is a format, think of it like a CSV for big data. We don't have time to do it like that. Just load it into the 3 cloud storage, and then with tooling and discoverability, just made it available for anybody to call it, to use it like I would just display. So here's my statement. COGs for vector data sets will be Abro files with simple features stored in cloud storage and activated in cloud data warehouses. And that's what we've done already on Carto with our data offering. So we've actually seen a massive like improvement from our previous systems. So I'm gonna stop it there. Thank you.
Awesome. Thanks so much, Javi. Yeah, in my talk at the beginning, I gave a little hint about the notion of cloud native vector storage. And I think, yeah, Javi definitely really articulated the potential for that. And yeah, I'm hoping we can figure out what that format is, that equivalent of the COG that every provider has available. So yeah, if you're interested in more of that, I'm sure will be a continued discussion in this community. And now over to Phil. Let's talk about Astraea.
Hi. Hi, my name is Phil Varner. I'm from Astraea. We aim to allow people to do analyses similar to what some of the things that Google Earth Engine does in doing large-scale, both temporal and spatial analyses of data. And we rely heavily on COGs and STAC API to power a lot of the components in our system. Without COGs, we would basically have no performance, from things as simple as generating a Slippy map on demand for a map while a data scientist is trying to explore the data that's available and look at what's available to them in a catalog, to even something as simple as generating a thumbnail on the fly. COG overviews really enables us to do that quickly and on the fly instead of having to spend a lot of time pre-generating and storing a massive number of preview images at different sizes and different scales, even doing compositing of layers and things like that is really fast with COGs and range reads and overviews. STAC API really enables a lot of our behaviors in both our UI that you just saw that allows a user to look through the data in a catalog, and in our Python, our Jupyter notebook environment that we call Earth AI Notebook. Users can investigate in the UI, export queries to a notebook environment, and then actually get a pretty similar view in the notebook environment. The STAC API allows us a really consistent interface among those things and allows us to even incorporate other tools into the ecosystem so that a user can use ArcGIS if they wish, or whatever other QGIS with the STAC extension, any other tool that happens to use the STAC API formats, or even GeoJSON formats that the STAC items also implement. Here's another example of a thumbnail that's generated on demand. If you look at this table and squint, you see that this actually represents all the things that are in a STAC item. And so an API can be transformed into these native Python concepts, and then transformed further into, in our case, raster frames, so that it can be run at scale on a Spark cluster. In running these queries over large amounts of data on a Spark cluster, the STAC API not only gives us it itself gives us a good way to query that data and find exactly the data that we need based on space, time, for example, cloud cover, resolution of the data, type of data, all these other dimensions. And then COGs allow us to do range reads that make it fast and breaking up all this massive task into lots of little tasks that operate on small areas of the data, can read only what's necessary to do that small operation, and then assemble them at scale. Yeah, so that's a little bit about how Astraea uses COGs and STAC API. The standards have been great for us because it allows us to hook into a lot of tools like GDAL and not have to reinvent a lot of that stuff. It gives us a really, really solid API that's not only supported with tooling, but handles a lot of the edge cases that if we were to have custom developed their API, we may not have thought of. And it's a great community to be part of. Thanks for letting me speak.
Thanks so much, Phil. You want to stop share? Cool. Frederico.
Yeah, I'm here.
Cool. Yeah. Cool. We see it. Go for it.
All right. So my name is Fred. I am CTO for MS Kepler. We are a company in Brazil that developed the software for the ground stations for the CBERS mission. And I'll talk about our experience in ingesting this data sets into AWS. So basically, I'll be talking about two different stacks. The first is responsible for transferring the images from Numpy to AWS and the COG conversion. And the other is making this imagery available through STAC. So we both create a static catalog but we also provide the STAC API. And this stack, I'm using STAC, but this is STAC Cloud Stack, right? Not STAC, the metadata. Yeah. So this stack also provide STAC. And most of the information about the data sets overall, you may obtain from the RODA on AWS. So this is the first stack. It's responsible for transferring the images. And basically, it simulates a request to the INPI catalog. The user receives then an email. This email is interpreted. And then the system downloads each band for the query and convert them to COG. I'll just talk about the key features or key points that I had to deal when I was working with this architecture. The first key point is how to deal with resuming failed downloads. So for instance, you have a Lambda function that is download data, sometimes it fails, so I have to restart it. And sometimes you have to synchronize the processing. For instance, I'll generate the quick looks only when all the bands for that scene is available. So for that, I use the step functions. So it's a way for you to synchronize all that Lambda processing and keep things manageable. The other way, the other thing is about the COG conversion. We use the AWS batch. It's based on Docker image with GDAL. And the interesting thing about the batch is that you can define priorities for your jobs. So for instance, you could have, when you are downloading all the archive, there are a lot of scenes, and maybe you want to prioritize the scenes that have less cloud coverage. So you can do that. So you have a single queue, but you have different priorities on the jobs, and then the jobs that for the scenes with less cloud cover, you could process that first. So that's something interesting. So about the second stack, which is the stack that provides the stack items, one key point is how to notify users that there is a new item available. So the way we do that, I hope you can see my pointer here, because I will be pointing on the graph.
Yeah, we can.
Yeah. So when this is XML data, this is the metadata from INPI. So the first thing is that whenever this data is put in an S3 bucket, there's a Lambda function here that converts that to stack, place that on a stack bucket, and notifies through this SNS topic about this new item. So you could have an application here. This SNS service is public, so you can have a client listening to this point, and then getting notified whenever a new item is available. And in addition to, let me just check here. So the payload for that message that goes into that notification service is the stack item itself. But I also add as an attribute of the message, the bounding box. So you can see here. That way, if you're a client, you can subscribe and define a single point and make AWS apply that filter before even notifying you about that message. So you can do a very rough geographic filtering on this data before even you receive it, right? Another key point is how you update the static catalogs. You have to do some sort of synchronization here to do that. And the way I did is to adopt a lazy approach. So instead of each item, when you add, I have to update the collection and the all collections that's related to that item. So a way to do that is using DynamoDB to make this synchronization easier, right? I'm a little bit of, don't have much time here. So another key point is everything in this architecture scales very well. So serverless, when you have a high load, everything scales, except the Elasticsearch engine that I use to provide the API service, the dynamic API service, right? So one problem with that is that if you listen to messages from the topics and then insert these messages into the Elasticsearch search service, if that rate is very high, it's probably possible that your service can deal with that. So you start to have a lot of errors. This message need to be reprocessed and have a problem. So the way I did to solve that is to throw the lambda of execution with the reserved capacity. That way you can say that the maximum simultaneous executions for that particular lambda function is 5, for instance. And that way I keep my Elasticsearch with a load that I can guarantee that it doesn't have problems. About what's next, right now we are working on extending the data set with CBERS 4A scenes, right? The new thing about CBERS 4A is the WPM camera. We have also the WFI and the MUX camera, but that's basically the same camera that flew on CBERS 4. But for WPM, that's the first time you have an open data set with that kind of resolution. So we're talking about 2 meters for panchromatic and 8 meters for multispectral. It's systematic cover over most of South America. I'm also working on full 1.0 stack support and distinction for some open software that uses these data sets as the CBERS GIF, which is a tool that generates animated GIFs from the data on AWS, and also RealTiler PD to allow the RealTiler to work with CBERS 4A. And that's it. Thanks.
Awesome. Thanks, Fred. Next up, Stephen, are you online? I don't know that I saw you. We were trying to get you scheduled in the afternoon from this in the morning. If not, speak now. I will bring you online. I didn't see him in the list. If not, we'll do a pre-recorded talk from Marten from Esri that I will attempt to play, and hopefully we get volume. All right. Let me know if this does not work.
Morning, everyone. My name is Marten. I'm a consultant with Esri and have been working on data discovery for over 15 years. During that time, my team and I have developed the Esri GeoPortal server, an open source product for discovery and use of geospatial resources. The product has been used by many organizations across the world to deliver search capabilities for a variety of content types and technologies. GeoPortal server includes a catalog built on Elasticsearch, and it allows for configuring different indexes and search experience for specific use cases. From its inception in 2003, GeoPortal server has implemented standards-based metadata and search specifications. Crawling content from a federation of catalogs has led us to develop a specific harvesting application. The harvester can go out and collect content from various sources and build a single index of all of that content. When working with catalogs at different levels of government, we have seen a clear relationship between those levels and the size of the catalogs. National catalogs, such as data.gov, typically include the hundreds of thousands of items, and commonly those are harvested from lower levels of government, states, cities, counties, etc. However, all of that mostly focuses on dataset and web service metadata, described using traditional ISO and FGDC metadata specifications. In our work with a number of federal agencies and looking at the data lakes of today, we uncovered a new, much larger type of catalog and data discovery realm. Earth observation data, be it satellite-based, survey-based, sensor networks, provide a different challenge for data discovery implementers. When asked how you find a needle in a haystack, I always say, that's easy, use a magnet. Finding a specific needle in a stack of needles is much harder because all of the needles look the same. This has led us to look at search facets specific to types of content in the catalog, as seen here between a traditional metadata catalog on the left and the catalog I'm about to show on the right. Indexing Office documents would itself bring different types of search facets and filters with it. Using GeoPortal with STAC requires really two things: The first is to create a catalog of stack items. As a prototype, I implemented a simple crawler of stack sources using the nest structure of stack. It is actually very similar to a folder structure or the sitemap structure. I then construct a representation of that item in my index, picking and choosing those properties from the stack item and augmenting where possible. Lastly, I use the GeoPortal web service to put the item in the index, quite literally. I could run the script against multiple stacks and adapt this as the specification of stack is developing. Then I configured my GeoPortal search page to have the specific facets useful for this catalog, such as place and time, the source, which stack did I harvest the content from, cloud cover, day of the year, etc. Combining one or more facets then quickly allows you to zoom into the items of interest. Once you have found some, scroll to the bottom of the page and see a couple of links to get to that list in different types of formats, and then you can use those for analysis elsewhere. Here I have a simple Python notebook hosted in RHS Online. I create a set of queries. I have two sample queries here, one for a specific CBERS stack and another one that combines a number of facets. Those links that at the bottom of the search page you saw previously actually will create you this specific Elasticsearch query language. In the second block, I choose one of the two samples, the CBERS 4 example and this one. I choose where to start, how many items I want, and then I issue the request to the OpenSearch endpoint that will return a CSV file in the GeoPortal server. The content is then simply read into pandas, and you can use this for analysis elsewhere. Important to note is that while the example I showed here uses content from a single stack, the second example would use content from multiple stacks and looking at facets like place and time and cloud cover. I hope you enjoyed this little presentation. If you go online to the first link, the geos.esri.com/image catalog, you will be able to play with the example I've shown here. If you're interested in the GeoPortal server source code, you can find it at GitHub. From there, you will also be able to get the source code for the harvester tool. Thank you for your attention.
Great. I think and hope that worked. I should have checked. So yeah, thanks Esri for Marten for sharing what Esri is up to. Super cool to see. He tweeted that out last week and got him in for a talk. So cool to see that type of experimentation with existing harvesters. Ahmed, you with us?
Yes.
You want to share your screen?
You should see my slide now, right?
Yep, we got it.
Okay, yeah. Hello again, everyone. So this is Hamid with Radiant Earth Foundation. I have a quick slide about Radiant for those who might not know Radiant. We are an organization with a vision to basically revolutionize ML and Earth observation for global impact. And particularly our mission is focused on generating and sharing benchmark training data sets, standards and tools around usage of ML and EO, and to build a community around these technologies so we can have a better impact on solutions around global challenges. Particularly, our mission has been narrowed down over the course of the 4 years we have been in operation, and we are now focused on what we call an ML Commons for Earth observation. The first pillar of activity is a hub, which is Radiant ML Hub. And it has geospatial training data sets in stack catalogs. We are gonna expand that in the next year or so with a catalog of ML models. So open models that are developed on top of these training data sets can be accessed as well. We recently won a NASA cooperative agreement to expand on that. So very excited about that opportunity. We also run competitions, challenges on these training data sets, and data labeling efforts, including the contest that I talked about earlier in the morning. The second pillar of activity is basically this event today, the community, convening the community around standards and best practices. We have a technology fellowship. Chris has been a fellow from the beginning, working on open source activities. Robert Manuel from Xavier is the other one, and Brookie Williams from WRI. So supporting these kind of open source activities is part of our mission. And lastly, the education and market information about what are the best practices and recent advancements in this domain, and providing that information to newcomers and the broader community who is interested in this topic. In summary, basically, Radian MLHub is a geospatial training data repository. It is all based on cloud. It's open access in the terms that anybody can sign up and start using the API. We have authentication because we need to basically have a confirmation from the user that they will follow the dataset license. In case, for example, it is not CC by 4, it is CC by Share-alike or any other one. But in general, the data and the API both are open access and anybody can self-sign on. As I mentioned, it's an API access, so we have a STAC API for all these data, and everything is a STAC catalog. We have the training data sets that have time series elements, or those that are just based on single snapshots. This is just a quick overview of the data sets we have. We released a massive data sets in July, land cover net, which is the first version of our global data set for land cover classification using Sentinel-2 time series. The first version covers whole Africa, but we are going to add the rest of the world to that. It is an image annotation product, and it covers 7 classes based on the time series. We have several crop type data sets, mostly in Africa now, and we are expanding on those. And the other element is what I call here partners data. In many cases, we host data or add the data to our registry, which is completely generated by another partner organization. The Microsoft AI for Earth Chesapeake Bay land cover data, the 6 SpaceNet data sets, the big EarthNet from the TU Berlin, another few moisture data set from Sentinel-1 on Landsat 8 from Stanford team. And you can see the description of all of these on our website, registry.mlhub.earth. I also have a tutorial which I will go into more detail about how the API works, how you can access it, an example of the Jupyter notebooks we have for accessing the data. So you can join later today at 2:20 PDT. Yeah, and with that, I will thank everyone. Thank you, Chris.
Awesome, thanks. Stop sharing. And Kyle, you with us?
Yes. Let's see if I can share my screen.
Yep, I see it.
Okay. So I'm Kyle. I work at Unfolded, but today I'll be talking about a personal project I've been doing to bring cloud-optimized GeoTIFFs, especially the Landsat 8 archive, into the browser for visualization with WebGL. So here you can see a false color composite of infrared imagery overlaid on 3D terrain at the Grand Canyon. Sorry, the GIF compression got a little messed up. So first, why am I excited about cloud-optimized GeoTIFFs? Well, cloud-optimized GeoTIFFs support efficient data streaming, as you know, and there's huge collections of data, now Landsat and soon Sentinel-2 data, publicly available on S3. So I think that the browser is the future of data visualization, but that presents a big problem of how to move data efficiently from the cloud to the browser. So some projects decide to request GeoTIFFs directly from the browser. But I find that that's inefficient, especially when you are rendering a mosaic of images, because each image has its own latency for each part of the GeoTIFF. And then you also have to figure out how to combine and reproject those pixels in the browser, which is a little complex. So I put a compute layer, AWS Lambda, in between the GeoTIFFs and the browser. So this compute is close to the data. It can combine and reproject the data to Web Mercator and then send it back to the browser where I can do interesting stuff in the GPU. Historically, rendering of image data would happen on the server. So say you wanted to request a true color image. The server would take the red, green, and blue bands and combine them into one image to send back to the user. But I'm doing client-side rendering on the GPU instead. So I request the red, green, and blue images separately and then combine them in the way that the user wants on the GPU. This is helpful because with client-side rendering, if I want to add pan sharpening, then I only need to request one additional image, whereas the server-side rendering approach would need to request 4 images from the archive and then combine them into one image to send back to the user. Additionally, with the GPU, I have a lot of flexibility in how I combine these bands that I get from the server. So I can combine them in any way that I want. I can combine them in a false color composite, say an infrared false color composite, or I can compute vegetation indices on the GPU. And helpfully, because these indices use the same bands of data, I don't need to do any new server requests every time the user decides to change something in the visualization parameters. This is also very extensible for new algorithms. Any algorithm that works pixel by pixel is very easy to implement on the GPU and is very easy to do in the same manner. I also have a lot of image flexibility because I'm reading from cloud-optimized GeoTIFFs. Because I'm not doing any pre-generation of images ahead of time, I can choose to read. So here you're looking at false color forest burn composites before and after the large Eagle Creek fire in Oregon in September 2017. And because of this flexibility, you can see how the land heals over time before and after this fire. So thanks, this is possible because of USGS, AWS, and others, and many thanks to Vincent Sarago and Jeff Albrecht for advice. This application is open source and publicly available at landsat8.earth, and I have more information on my blog and on Twitter as well. I guess I went a little under time.
Yeah, I was like, you get the prize.
I really didn't want to go over 5 minutes.
I appreciate that. Yeah, thanks so much, Kyle. This was awesome to see. Cool. So next up, we've got Leo.
Hey.
Hey.
Can you hear me?
Hear you. See you. Do you want to share your screen?
Awesome. Fantastic. I'm going to use up that time that Kyle didn't use. Sorry, let me just try to share my screen. Oh, man.
No, you have to enable.
I have to enable some permissions. It's going to ask me to quit Zoom. I can reconnect in just a second.
Yeah, go for it. Well, we have any questions for Kyle? Actually, I have a question for Kyle. Can you tell us a little more about the format that you're sending across?
Yeah, so I had some issues working with 16-bit data on the GPU. So for now, I only use 8-bit data on the GPU. So I send JPEGs right now to the browser, each band individually, and then combine in the browser. You can also send 16-bit PNGs, which I was experimenting with, back to the browser. It's just some newer GPU technology that you have to use that isn't supported on all browsers, for example, Safari. But yeah.
Cool. Yeah, I think Duck is also talking about this in Bit from Planet, and yeah, I'm super excited to figure out what is this format that we send across. Yeah, hopefully we'll see some there. All right, Leo, we see your screen.
Cool. Okay, can you see the slides?
Yep.
Awesome, fantastic. So my name is, sorry, good?
Yeah, it's all you.
Okay, let me just start my timer here. My name is Leo Thomas. I'm a data engineer with Development Seed. I've been working with NASA on the commercial smallsat data acquisition project, and my focus has been on integrating radio-occultation data produced by Spire into this, into this project. So I want to talk a little bit about some of the successes and failures we've had with this project, which definitely has felt like fitting a square peg into a round hole at times. So a quick background on what radio-occultation is. It's a technique that involves a low Earth orbit satellite that you can see over here on the right-hand side of the planet, communicating with a GNSS satellite up in the upper left-hand corner of the image. As the two satellites communicate, the signals will pass through the atmosphere or the ionosphere, and either will be bent by the atmosphere or the phase will be shifted by the ionosphere. And depending on how much this signal is bent or shifted, you can derive knowledge about the atmospheric conditions at that point. So things like temperature, pressure, humidity in the atmosphere, or ion content in the ionosphere. The ionosphere is just a layer outside the atmosphere. This data set's fairly complex. There's about 14 different data products that we're working with. It generates about 100,000 different files per day. These files are organized into a fairly complex processing chain that we think about in two major parts. There's the low-level data that's kind of very close to the satellite sensors, and then the low-level data gets processed into higher-level data that we call the RO profile. So this is the actual temperature, pressure, information of the atmosphere, and the ionospheric profiles. So again, ionospheric information. And this is the kind of data you could put into like a weather model or a space weather model. Some of our goals with with this data is to make it accessible and useful to a wide variety of users. So kind of like what Chris was mentioning this morning, we have a lot of the users that are currently using our radio-occultation data, or RO data, are downloading all of it, duplicating all of it. They request 6 months for the entire Earth and then parse it themselves. So those are users we want to target with this, in a more efficient and streamlined kind of streaming way. We want to target users who are just interested in the high-level products, like the RO profile and the ionospheric profiles, but don't necessarily want to interact with the lower-level products. And the opposite of that, some users might have applications that are completely unrelated to radio occultation, but for some reason or another, they're really interested in this low-level satellite sensor product. Lastly, we'd also like to maybe make this data accessible to users that don't even use radio occultation data for now. And just haven't been able to use it because of its lack of accessibility. So some of the challenges we've had in fitting this data into the STAC API, a lot of them stem from the fact that radio occultation data isn't really pointed towards Earth. A lot of it has to do with conditions in the atmosphere, above the Earth. So the idea of bounding boxes and geometries becomes kind of hazy. This data doesn't all translate very well into lat-long points on the surface of the Earth. Another challenge of this, this data is that not all of the data is georeferenceable on its own. A lot of the lower level data products just have to do with the satellite sensors as the satellite orbits the Earth, and that gets processed into data that is georeferenceable. But how do we make this lower level product accessible through the STAC API when it doesn't really have its own geometry, or it doesn't have a very clearly identifiable geometry? In this same idea, some of the data isn't necessarily useful on its own, or it's not useful to everyone on its own. So we've had a lot of questions about how do we bundle data together, and what is going to make, what is a useful bundle of data to present to users without making it unnecessarily complex to parse for certain users who are only interested in certain data types. So our solution has, we fit this into a STAC API. What you can see here on the screen is sort of a subset of the data that we fit into the STAC API. What you'll notice is that each box is a separate STAC item. And we collect different data products into a single STAC item. This is kind of our best guess at like what data products are useful to be distributed together. All of the boxes are the same color, inherent or assigned the same geometry. So this allows us to get away from the problem of, for example, these open GNS files don't really have a very clear-cut geometry. We can assign them the geometry of the atmospheric profile that they eventually get processed into. And then lastly, we use the derive from link in the STAC items to represent the relationship between products. As one product gets processed into another product, you can follow these derived from links to kind of view the entire processing chain. So the last thing I wanted to leave you guys with is just kind of a gift from our data explorer. What you can see is this first point geometry appearing is a radio occultation profile. So atmospheric conditions over a single lat-long point in the atmosphere. And then that second track that's appearing is what we call like a navigational item. So it's all of the data that has to do with the satellite sensors as it orbits the Earth. So that's a little bit about radio occultation data and STAC. Thank you.
Awesome. Thanks, Leo. Yeah, I love seeing data that's not what we originally imagined fit into it. And yeah, definitely let us know if there's tweaks needed to the spec to support it. But yeah, looks like it's.
Absolutely.
You want to stop sharing?
Yep.
And Daniel, are you with us?
Yep, I'm here.
Awesome. You want to share?
Sure. I was just working on it up to the last second.
Nice.
So hopefully it goes well. I'm sure many other people did as well. So hi, can you hear me?
You're great. We see it.
Cool. So edge compute, cool term. I'm going to show some edge compute in action and cool stuff you can do with COGs in the browser. I know I'm not supposed to do live demos, but I swear it will take like 1 minute and it'll be quick. The architecture that I'll be showing is really simple. You have your data in Amazon S3 bucket, and then you have your web browser. And the web app makes HTTP range requests directly to S3 and renders the data. What I'll be describing is using and describing is this library called GeoRaster layer for leaflet. This is a leaflet plugin. Some of the features are it does sampling to render the image. So it's not going to render the image in the full resolution. It uses web workers like any good JavaScript project. It will visualize really large GeoTIFFs, which I'll show in a second. And you can also do custom rendering, band arithmetic, coloring in the browser. And then it also runs on the CPU. So you don't have to have your WebGL enabled. So here's some examples. You can go to this link. Can you still see my screen? Yes, sure. Okay, cool. So we'll give an example of NDVI. So this is pulling directly from Landsat 8 and doing band arithmetic, near infrared minus red over near infrared plus red. And it's doing the NDVI calculation in the browser. You can zoom in, and then it's going to do the calculation again. Here is one for wildfire analysis. This was from some old imagery. It has a Landsat 8 scene, and then it is finding the pixels that have a certain signature that have the values that indicate that there's a wildfire there. And you can see that the white in the top that's the smoke. And then there's visualizing population. And this comes from the GHSL Copernicus data. And that's just the population raster being visualized. And then there's a bathymetry data too, which is a really great data set that I recently learned about. It's based on Gebco, and Tom Patterson did some work on top of that to clean it up and make it nice and easy to visualize. And so that is pretty much my presentation. If you have any follow-up things you'd like to discuss, you can find me on GitHub here. Thank you.
Awesome. Super cool. Yeah, I think somebody actually asked this morning about leaflet and GeoTIFFs and direct COG. So super cool to see this. Daniel, do you want to drop that link for the demos in the chat so people can click on it and explore on their own?
Will do. Thank you.
Cool. Thanks, Daniel. Scott, you with us?
I am. Hi
hey.
there. I'm working on sharing my screen here. Just a second.
Yep.
There we go.
Looks good.
All right, great. I'll jump into it. Thanks for inviting me to this. It's been great so far today. I'm Scott Henderson. I'm a research scientist at the University of Washington. I work in the Department of Earth and Space Sciences and the eScience Institute, which is a data science institute at the university. So I'm going to give a quick overview of the Intake-STAC library. Oh, sorry. There's a link, short link here on the first slide if people want access to the slides, and I'll make sure that goes into this Zoom chat after this. I work a lot with the PanGeo project, and I just want to give a super brief intro of what PanGeo is in this lightning talk. There's a link to the website here with more information, but it's a really great community resource for big data and geosciences. So this has been a huge resource for connecting scientists with professional software engineers, and the work I'm about to show on Intake-STAC is related to this overarching effort. Specifically, the Intake-STAC library came out of a NASA-funded project to improve search discovery and interactive analysis of satellite data. So satellite data in general, but in particular raster data. And this schematic on the right on this slide kind of illustrates where the scientific community is at in terms of interacting with NASA data sets, where on the top we have this current model of interacting with specific APIs for NASA archive centers, downloading data and working on our laptops for whatever sort of analysis we're doing. But as more and more data moves to being hosted on the cloud, there's an opportunity, as we've seen from many presentations today, to switch the way we're computing, move algorithms to the data where we can take advantage of scalability of the cloud. So with the PanGeo project, we've set up several Jupyter Hub systems, so using Jupyter notebooks to interact with cloud-hosted data sets. And in contrast to some of the other platforms we've heard about today, we've been focusing on using Dask clusters for distributed computing behind the scenes, and using just a combination of fully open source software and infrastructure. So it's a pretty unique project. I encourage people to check it out. So the first thing you want to do when you log into a system like that, or you're using a Jupyter notebook, is find data and work with it. Currently, this is a bit dated, but just a table of open data on AWS, where we have a bunch of sensors on the left, various formats, potentially in different regions within a cloud provider. And so we want to connect scientific users with these data sets so that they can run analysis. And there's a tremendous number of software libraries in Python that are well established. And the goal with Intake-STAC was to connect existing software to work efficiently together. So the way this works is we start with a stack catalog, spatiotemporal asset catalog, as what's hopefully a standard among the many imagery providers putting data on cloud storage. Intake is a Python-specific library for data catalog management, and Intake-STAC connects the two. So it facilitates exploring catalogs and bringing data sets or stack item assets directly into an interactive Python session for computation. So this would be an X-array object or Numpy array, familiar data objects. So Intake is this system that combines cataloging and has a notion of different data drivers for various data types, or and also convenience functions for mapping various data types to different objects. So just a quick couple of examples of how this works is in a Jupyter notebook, we import Intake, and then Intake-STAC is connected behind the scenes so that we have the ability to open stack items. So in a line of code here, we're pointing directly towards a stack item in a catalog, and we can immediately extract assets. So this is a Landsat item that has many bands, and we can load that item using a toDask function that gives us an X-array object back that we can compute and run distributed computations of our choosing on. We can also use search utilities. So we've heard about some different stack APIs. One of them, one option for searching is Earth search, put together by Element 84. So we can search a particular stack catalog based on a bounding box and time, and give back a browsable interface to these various items and bands. And again, we can bring those items directly into X-ray objects.
Cool.
So one quick illustration, just how this works. Once we have X-ray objects, we also have the ability to do interactive visualizations. So this is using HoloViz tools for browser-based visualizations, where we're loading cloud-optimized GeoTIFF, as we saw earlier, directly to X-ray. And once it's in X-array, users can do whatever they want with it. Visualize different bands, zoom in, and the resolution's updated based on your zoom level. So this was a very quick whirlwind tour, very much a lightning talk, but pretty soon at 1:40, we'll have a 40-minute outreach session. So my hope is to get people actually using this. And then there's some other links here to various recordings and whatnot if people want to learn more about this effort.
Awesome. Thanks so much, Scott. Yeah, and honestly can dig in to learn more at the intro session, which should be a good one. Chris Helm, you with us?
Yeah, is it my turn?
Oh, no, I'm wrong, sorry.
Yeah.
Sorry. Just keep me on guard. Duck, are you with us?
Yep. Can everybody hear me?
Didn't mean to skip you. You want to share your screen?
Yep, working on it here.
And yeah, we can hear you. Awesome, we see it. I can give a quick intro. Duck works at Planet with me. We used to work on the exact same team probably 9 months ago at this point, working on Explorer. And yeah, I think he actually started this stuff back then and working to bring it live soon.
All right.
Cool. You ready?
Yes.
Cool. Is it showing up on the screen? Zoom's giving me weirdness.
Yeah, we see raster data tiles.
Okay.
Yep.
Like to thank Chilms for the introduction. And in fact, before I even get started, I wanted to give a shout out to my coworker, Ian Schneider. He started some of this work before I was even at Planet and has been my partner in crime on getting this going. So what I'm going to cover is how we're using COGs along with Numpy and OpenLayers to do some of the client-side raster data work. So like Kyle covered and Daniel certainly ran into, browsers are really only into red, green, and blue, and they really only like, generally speaking, 8 bits per channel. But our satellites, like everyone else's, aren't really into that. We're getting much wider pixel depths. So our general solution for how we do that is we apply what we kind of call a global color curve, which is nice in that it makes all of the imagery that goes out really, really consistent, but it doesn't give you a particularly good view in a specific location. So to misquote the notorious BIG, the mo formats, the mo problems. WebP, JPEG, PNG, they all have that real 3-band limitation if you're trying to bring all of your bands in at once. Well, the solution that we've seen earlier today is to bring COGs in, but when we're doing that
at like a full view scale, we noticed that it got pretty crashy. We had a lot of browser sadness, particularly when we sort of kind of scaled it up and added more and more bands. So we decided to try and use a freebie and developed a format that we call the Numpy tile. For those who aren't familiar, Numpy, or numerical Python, is the Python library for doing lots of big array math. A Numpy array is its native data type. Well, in our processing chain, what we've been doing is taking the COG data, loading it into a Numpy array, applying the color curve, and turning it into a ping. So we asked ourselves the question, what if we just skipped step 2 and sent a 256 by 256 by whatever depth array to the browser? Well, turns out it works, and it hits like the holy trinity of cheap, fast, and easy. It compresses really nicely over the pipe, just using gzip compression. And Numpy arrays in Python translate really, really easily into typed arrays in JavaScript, which you can also feed into WebGL. To bring it all together into a map, we use an OpenLayers heavy stack. So we wrote a custom OpenLayers layer and source that inherits from the image tile class, so it fits right in and works like a normal OpenLayers layer. One of the cool tricks that it lets us do is what we call snow mode. So with the regular color curve, we don't get a lot of depth there, but it brings in the data and applies a new color curve based on the scene, along with some other tricks specific to snow, and provides the additional contrast. Now, all of the screenshots that you're seeing here, all of the clips, are happening in real time. There's no trickery, skipping the frames or anything. So you can see that loaded all the data, it computed it, boom. You got a new color curve with greater contrast, so you can actually see the details in the snow. One of the cool places to test some of this is the state of Oregon, because you can go from snowy mountains to green forests to basically desert areas in not a huge area of land. And so you can see here we have some snow, we have some greenery. Now we're getting out onto kind of the deserty plains. And what you're seeing is, as you pan the map, it's computing the color data at full bit depth and creating a new color curve to actually apply it to the scene view. Now, at the same time, we're also capturing all of the additional bands. So we are getting the NIR band in and have the ability to do things like NDVI and whatnot, but I didn't have that together for today's demo. Some future work that we're looking at doing with it, one is to improve the performance and get things working a little bit better with WebGL. I think everybody just wants to make their code faster, and we're definitely in that camp. The second is we're looking at using the tiles to actually provide the client-side ability to do data inquiry. So like the idea of, I want to draw a polygon on the map and I want the NDVI histogram for like this chunk, because we have all that data there. The other thing we're looking to do is document. While we have a package up on NPM, the @planet/dynamic tiles that works with the format, we want to do a little bit more work to get everything useful for other people. All right, thanks folks. That went really fast.
Awesome, thanks so much, Doc. Looks great. Chris, now you're actually up.
Now it's my turn. Can you hear me?
Yep, I hear you.
I knew something was off when you called.
Like looking at my phone and it just like scrolled slightly past it. I was like, oh.
Yeah. Let me give me a second here.
I'll give you a second to give a warning to Amy, which I think, wait, well, one, David Raleigh, are you online? David hasn't made it. So Amy, you're going to be up next right after Chris, hopefully. If not, I can play the video. We see some screen now, Chris.
You see it? Okay. Well, thank you for having me. My name is Christopher Helm. I work for a company called Pixel. We're a new company. We are working with point clouds. So I will not be talking about COGs in the browser, which is all been blowing my mind for the past several talks. I used to work for a company called Maxar. At the time, it was called Digital Globe. We did a lot of things with Python and arrays and all that's hitting home, so I'm loving it. But now my life has shifted into point clouds. So we at Pixelate are building a 3D map of the world. And the 3D map of the world that we're building is both for human consumption via visualization, but also for machines, right? And how machines might consume these point clouds is the topic that we'll be talking about today. But just some introduction to Pixelate. What we're doing is we're taking photos and videos and commodity products and constructing point clouds and fusing those point clouds into a 3D map. Now, that's a pretty loaded conversation that I'm not going to get into fully, but what we have here is a bunch of small point clouds that were taken to my town, Salida, some time ago that are fused together and then geo-registered to a common baseline using bundle adjustment, a procedure that we allow to align our little tiny mini point clouds together. So what that looks like when we start sort of dissecting those is we've got these little areas of the globe right now, except we're an early company. We don't even have a public API at this point, but it's coming really soon. So anyway, we have these point clouds here. We can see that a bunch of them are these tiny little things. If I colorize them by each point cloud, what you're seeing here is this underlying sort of separation of these entities that we treat as a unit of currency inside our API. And so naturally, it makes sense when we start thinking about, well, how are we going to start exposing this API via something like STAC, that we would want to use these small little units of currency. And so what we've done is we've built an API, and this is all super nascent. I'm just showing it because we've done it, and it's kind of cool to us. But so we've exposed this API as this list of STAC items. And what it allows us to do is just, okay, now we've got this thing that's STAC compliant. We put it in the STAC browser, see where we have clouds, allow others to search it. When we have an official public API, we'll start making more use of these things. Each of these items links back to the page I was just showing you, the stream, the data you need. You can actually download the LAZ. But also, each one of these clouds is accessible in a format that's called Entwine. And Entwine is a cloud-native point cloud structure. And so it's not necessarily a format, but it is a format. It's an tree-based tile structure that sits on the web and can stream trillions of data points, right? And so we can build these massive structures in Entwine and then stream them over the web, not having to download the entire thing, but download bits and pieces that we want to know, right? We can access stats at the high level. We can access little bits and data and pieces when we want it. It's very, very, very similar to a cloud-native GeoTIFF, right, or a cloud-optimized GeoTIFF, but it's point data. And so this comes into play when we start looking at some of the data we have in our system that are larger than these tiny little point clouds, which actually fit pretty well. They're a meg or 2 megs. These now start to be 50 million, 60 million, 100 million points in the browser. And that wouldn't be possible by just loading all, several gigabytes down. And so access bits and pieces and see that it'll load in. I don't know if my browser in Salida here where I'm at is going to support me pulling too much data right now, but it's and also the curse of the lag demo isn't breaks, right? What you see here is that we're looking at a point cloud that we've constructed over Boulder from aerial imagery that's being fetched down slowly in these small tiles. But again, I'm in the middle of the mountains. It's really, really slow. But something we rely on as well, besides just these point clouds here, is LiDAR data. And this LiDAR data allows us to have sort of a baseline. And the baseline is collected by USGS. This is their 3-dev data program. It is all living on AWS open data, right? And so with all this data out there, we have the need to fetch this data down and think about it from a standpoint of, if a user in the middle of Wyoming fetches it, do we have reference data there? Can we bind and tie up their point clouds and their photos onto those onto that reference set? And so, and actually, I wanted to pivot back and talk about, so I was supposed to go Entwine into Poodle. And Poodle is something that is very similar to something like GDAL, right, or Goodle. So for all the COG talk, this is our version of the point cloud land. So you have to give a shout out to Howard Butler, Connor Manning for Entwine. Typically, when we have Entwine data sets, we're using pipelines from Poodle here to construct these streaming pipelines and doing things like reprojection and filtering and culling out points and stuff like that. But like with Entwine and with Poodle, like come this idea, this need for searching and accessing all this data living inside the USGS 3D buckets. And what those look like is this, right? Each of these is a single entity, but they're individual. I don't know if I have them pulled up or not. Let's see what they look like. They have individual sort of like their own structures to them, right? They are like, you know, a single cog. We'll see if it loads or not. Come on. Oh yeah. All right. So it's there. All right. So we can pull it up and we'll watch Poetry do its thing. It'll start loading. It's nice and pretty fast and pretty good. It loads in lots and lots of data. We can sit here and make it look prettier for no reason other than, I guess I'm killing time at this point. No. Yeah, so that's our cog, or that's our version of a cog here. It's these Entwine data sets. And so during the last stack sprint, what we wanted to do at Pixel 8 was say, okay, we have all this 3dep data and we need to access it, we need to search it. Our first intuition was, oh, well, shoot, we'll just pull down the boundaries, the GeoJSON, we'll dump it into our PostGIS database, and now we'll start serving up our own indexes. Gosh, that's kind of lame. What if we could just access it via stack, like a remote catalog that also lived on AWS and we didn't have to touch, and we could keep it up to date and always live? And so we went down this path of saying, well, okay, we've already done the work for taking point cloud extension to this stack spec and applying it to our own API. Well, let's go ahead and just basically swing through the 3dep catalog and apply it. We get there and say, okay, like this is actually still a proposal. So there wasn't actually any implementations other than this one example of the stack spec for the point cloud extension. So we're, okay, we can do that. But pretty quickly we realized there's no tools, and so we just kind of left with writing JSON. But the last stack sprint was a software sprint. So we went ahead and added this point cloud extension to PyStack, and which was a good experiment because it just helped us flesh out what it meant to be adding something to stack. You know, do we have projection here? Well, no, there's another, you know, extension, things like that. Just for our own learning and growth, we're learning about, you know, how to do this. And so this actually turned out really well, and we leveraged this point cloud extension to PyStack and went ahead and let that drive our development for the sprint. And what we ended up with is a stack catalog of all the 3dep data. And I was plugging this into the browsers. I haven't pulled that up yet. I'm just looking at the JSON here. But what you can see is we've added the schemas for the data, the encoding, right? These are the things that start to make a point cloud, right, an official extension of Stack, is that it's got its own sort of schema, it's encoding these things that matter to point clouds like count, that wouldn't necessarily matter to a cog. And that's it. I was probably way under. I wasn't timing myself. I was assuming I was going to be short, but that's all I got.
You're actually over, but it's all good. It was great.
No way, really?
I forgot to time this one, but maybe you're good.
I'm under. All right, see you guys. Thank you.
We'll check the records. Awesome. Amy, you're up next.
Yeah, and we've done a little bit with end-time point tiles, so I was actually happy to learn more about that with that point cloud extension. I'm going to take it back into Raster land and talk about some cloud optimized GeoTIFFs we produced for AWS public data sets. So can you guys see my screen? Yes. Okay. Present. So yeah, back to cloud optimized GeoTIFFs. So this is something that I worked on with my colleague Rachel at Development Seed. And the project basically to convert cloud optimized GeoTIFFs and make them available on the AWS Public Datasets program, specifically to support the NASA Space Apps COVID-19 challenge. So this is something that we did back in, I believe, March. So what was the data that we were interested in? So for this particular project, we were interested in basically enabling people who are participating in this NASA COVID Space Apps Challenge with a way of understanding how environmental factors were being impacted by by COVID, basically, people going in and out of the, shelter in place orders, how that might actually be impacting things such as NO2, aerosol optical depth, vegetation indices. So these are some of the data sets that we looked into pulling into cloud optimized GeoTIFFs, and a little bit more information about those. So why we chose COGs, I think, we probably all got that message by this point, but focus on data access over a small area, web visualization, so faster loading in web browser, and dynamic color scales. So this sort of, this is the COGGeo XYZ sort of way you can test out these cloud optimized GeoTIFFs. So this is looking at how you can zoom in on the NDVI product, one of the NDVI products, as well as a way to do dynamic color scaling. So we were able to, use all these different color mappings. So yeah, it's a pretty cool tool, just able to add in the S3 URL of whatever cloud optimized GeoTIFF you're interested in visualizing, and then get some basic stats there. So what was interesting about this project, other than the use of cloud optimized GeoTIFFs, was working with, optimizing for users and working with the science team. So we wanted to optimize for data access on the cloud and data visualization. And so that we, and these products in the cloud, we wanted to make sure that we were basically making them both scientifically valid as well as useful for end users. So sort of this idea of analytics ready data. So we worked with a science team at Goddard Space Flight Center, and we included we only included a few variables, right? So a lot of these HDF4 netcdf files contained, hundreds of variables that people were not necessarily interested in the short term. So we included things just like the most pertinent variables, which I've included some details on in this slide. And then another, some other sort of science decisions, I guess, or analytics decisions that the science team helped us with. So, do we want to apply a scale factor? Yes, most ready for analysis, but a larger file, or no, smaller file size, but users need to know to apply the scale factor. And this is the type of thing that maybe we could be able to better handle by having good metadata. So basically telling people, letting people know that there is a scale factor applied or not, and why. A few more decisions that were interesting for both collections, reprojecting the MODIS projection, which has its own projection you can see on the right, aggregated MODIS tiles to a single global image, and for aerosol optical depth, selected only the most optimal orbits for each tile. So this AOD product comes with basically 6 bands, each representing a different orbit. And so you sort of want to pick the orbit which is the best representation of the closest to basically that particular point, that latitude, longitude point. So yeah, main ideas: converted to optimize for data access, data visualization, interest in a particular region. And we wanted to make decisions to best suit our end users' needs. And finally, just wanted to say that, the goal for this sprint is actually, the goal for this sprint for this project is to create some STAC records and API for these data sets, because there are none now. And also that in the session that's starting at 1 p.m. Pacific, I'm going to be talking more about another AWS public data set, but that is in ZAR. So I'll be talking a little bit more about ZAR in that session.
Awesome. Thanks so much, Amy. Yeah, definitely join Amy's session to learn more about ZAR and dig deeper. I'm going to try to join as well, since I've seen ZAR and believe in the potential, but it's like to learn more. Jérôme, are you with us?
Yep.
Hey, you made it. Do you want to go live, or do you want me to just play your video for you?
No, I can go live, I think.
Awesome. Sounds
You
good.
hear me correctly?
Yep, we see you. You want to share your screen?
Okay.
it's night here, so there is not so much light.
There was not light when I started this morning, so thanks for staying up late. I think you're our last European. Actually, you're almost last of anybody.
Okay, can you see it full screen?
Yeah, we got it.
Okay, perfect. So, okay, my name is Jérôme Gasperi. So I'm the founder of SnapPlanet, and today I will present you Resto and Rocket, which are respectively our stack and server and client implementation. So Resto is a search engine for geospatial data, and initially it was built to index and effectively search metadata within large collection of satellite imagery archives. It has been extensively used in production by many agencies to make their Earth observation collections open. And in particular, it is a key component of the CREODIAS, which is one of the 5 cloud-based platforms funded by the European Commission to provide access to Copernicus data. So it is written in PHP and backed by a database, a PostgreSQL and PostGIS database. And all the deployment is done through Docker and Docker Compose. And it natively supports OpenSearch.io and STAC API, and currently is aligned with the last Beta 2 API. And we plan to release the version 6 of Resto, which will be aligned with STAC 1.0 when it is available. So the base API provides endpoint to manage collection and item. So you can create, update, delete, and search collection, and the same for item. But also there is a built-in mechanism to extend capabilities through add-ons. And there is over 20 add-ons that are available, including user management and social networking function, which are notably used by the SnapPlanet mobile application that you can download and try on your Android or iOS mobile phone. So one of the key features of Resto is to add a semantic description to input metadata, thanks to a library called iTag. So iTag is a web service. It is developed independently from Resto. It's open source. So it takes as input a geometry, for instance, a satellite image acquisition footprint, and it intersects it against external information layers and returns a JSON document containing a description of the location content of this footprint. So in the above example, you see that iTag indicates that the input footprint is located in the southern hemisphere, in the tropical zone, on the coast of Western Australia, and mainly contains water and forest area. So concretely, what happens when you ingest an item in Resto? So first, an item is pushed to the Resto backend endpoint, and the footprint is used to retrieve the semantic location-based content from iTag. And so this content is used to compute dynamic classification. And the cool thing is that these classifications are provided directly as stack catalogs. So the user can browse the items from different views. So it can see a catalog of collection, of countries, of land cover, of season. So any kind of facets that are provided as automatically by this semantic classification. So this is a view of the previous Sentinel-2 item processed by Resto. So you see on the top the classical input metadata, basically the metadata from the satellites. And below you have the semantically enhanced metadata provided by the iTag description. And every semantic property is indexed within the database, so it can be searched later on. So GeoDIFFs output is a great format to read, but it's better when you have a client to handle it nicely. So we developed the Rocket client, which is a stack web client with some bells and whistles. So Rocket is a stack browser. It supports both static and dynamic catalogs. It provides a simple way to browse the collection and the catalog of a stack endpoint. And here you can see it in action, browsing the classification catalogs from the Resto endpoint. Also, a map view is provided for dynamic catalogs, and it supports the Stack Search API. It provides a base stack spatial-temporal search filters for all catalogs, but also additional filters for catalogs that support them, like the semantic filters discussed earlier. And some of the key features include also the drag and drop of additional feature layers and endpoint, and also a gazetteer service with both direct and reverse location capabilities. So you can try this at http.rocket.snapplanet.io, and if you have any question, you can contact me. And so feel free to contact me anytime you want. And thank you for your attention.
Awesome. Thanks so much. Thanks for staying up late. So I think the one last talk is a recorded one. Can you stop your sharing, Jérôme? Okay, thanks. I will attempt to play this one. This is about Pygeoapi from Tom.
Hi, everyone.
Is that working?
Yes.
Awesome. Cool.
I'm Philides from the Meteorological Service of Canada, and today I will be talking to you about Pygeoapi. Pygeoapi is a young project started in 2018 and primarily focused around lowering the barrier to geospatial data through developer-friendly APIs using current technologies such as OpenAPI, JSON, RESTful principles, and linked data. The project is heavily implements standards such as those coming out of the OGC API efforts, as well as obviously STAC. It is a young project, but we have a growing team of international developers and users. The project itself allows publication of geospatial data, whether you have vector data or raster data or STAC catalogs or geospatial processes. You can make those available in Pygeoapi through a configuration, and Pygeoapi is basically made available through the web primarily, and data can be accessed through the web as HTML pages or JSON pages, really lowering the barrier to the access to accessing data. So a core feature of the project is this robust plugin framework, which allows you to basically connect any kind of geospatial data to Pygeoapi and make it available to downstream clients, whether they're web applications or GIS applications or mobile apps or other applications for that matter. It's relatively easy to deploy with a minimal set of dependencies. It is a cloud-friendly project, so we do have implementations and examples of Pygeoapi used on AWS, for example, and other examples connecting to object storage or S3 and serverless technologies and so on. The core approach is that Pygeoapi makes available a Python-based API, which connects to data via the data provider or plugins that you see underneath. And once those are all sort of configured, then the geospatial data is made, or STAC catalog is made available through the web accordingly. A bit of a tour around Pygeoapi. Here's an example of a home page or a landing page of Pygeoapi, which is made available through HTML. There's also a JSON equivalent for any of these pages, obviously. Here's an example of our OpenAPI capability. Here's an example of publishing feature data through Pygeoapi. In this case, this is an HTML page with a simple map of some lakes data from Natural Earth. We've recently implemented the OGC API coverages support. So here's an example of some real-time weather data being made available through the coverage JSON format. A user or a developer is also able to publish geospatial processes through the OGC API processes standard through Pygeoapi just the same. Here's a JSON example of a process description. And now we get to STAC. So recently we implemented the spatial temporal asset catalog as part of the Pygeoapi core. We initially started working on STAC catalog support at the OGC features sprint in Washington in November of 2019. We put an initial implementation together, and we spent the following months thereafter working on getting a core implementation in Pygeoapi. So the basic setup of how STAC works in Pygeoapi is a user is able to point to a file directory tree, and a stack catalog will be created and made available just the same. So if we go to a live demo here, here's our Pygeoapi landing page, and here we can see we have a link for spatial temporal assets. So what we did here at MSC is we did a stack prototype of Pygeoapi on top of our real-time numerical weather prediction data. So this is our global model, our global deterministic forecast system, or GDPS. So here we can see that setting this up through Pygeoapi, the user is able to traverse down various directories. In this case, our global model has model runs, and each model run has a number of forecast hours. Each forecast hour has a number of weather variables that are made available through in this case Pygeoapi and STAC. So as we go down into the forecast hour, we see there's a number of different weather variables, and let's look for temperature. So for example, here's the actual spatial temporal asset around temperature from our GDPS. Along, as mentioned before, along with any HTML page, there's a JSON equivalent, which is made available. So here we can see that through Stack Catalog, it is very easy to make real-time weather data available that are constantly updated. We use a relatively simple implementation of Stack here, but we are looking into how we can make sort of real-time weather data as some sort of stack profile with custom sort of elements around NWP and weather-based EO data in and of itself. So anyway, that's a quick overview of Pygeoapi as a project, and that's an overview of how we implemented Stack and how Stack Catalog is supported in Pygeoapi. So thank you very much for your time, and I hope you found this useful.
Awesome. Well, great timing on both the lightning sessions right to the end of our hour. So this is the last time we're all together with the Outreach Day. I wanted to thank everybody for coming, especially the speakers for sharing all that great stuff. I certainly learned a ton, and I'm sure everyone else did, on a ton of amazing topics. We'll have intro sessions after this. Amy and Norman both did lightning talks here. We'll go deeper on a couple topics, and then we have 2 more sessions of 2 more tracks after that. And then, yeah, in 2 days, we start on the sprint where we'll all start to work on this stuff. I know everybody put up mentioned things they were going to do, so it's really excited to see those. We'll attempt to do a bit more organizing of how people can jump in, and yeah, feel free to start working on your projects tomorrow and Thursday morning Pacific time. We'll do a sort of check-in and see where everybody's out, and continue into next week. And yeah, the labeling contest runs through next week as well. So yeah, thanks everybody, and yeah, have a great rest of your day.